So in this example, you've got a 2 kilogram stone. For whatever reason, you're sort of whirling it around, holding it by a string and whirling it around in a circle. That's about a meter. So imagine, here's your stone. You're holding it in the middle and you've kind of caused it to spin. So it's moving around like that. The string itself is 1 meter long. So you can see that the radius that the stone goes around in is 1 meter. And we're told it's traveling with a speed of 3 meters per second. So calculate the tension in the rope if the stone is rotating horizontally on a smooth, frictionless surface. So this question is actually pretty similar to the other one, except in this example, it's not friction that's holding the stone in its place. It's tension, right? It's the tension in the rope. You can call it T or FT. But again, gravity is acting straight into the page. The normal force is acting straight out of the page, and they cancel out. So we only have to worry about one force, and that's T. And so when we go to solve this problem, we say FC equals MAC. MAC equals the sum of the forces. I can't emphasize enough that the physics of circular motion is exactly the same. All that's different is we have a new type of acceleration. If the net force was parallel to the direction this object was moving, it would either speed it up or slow it down. But since it's perpendicular to the direction the object is moving, it does not actually change the speed, it only changes the direction. So we use this new equation, mv squared over r. So AC, because AC equals v squared over r. So mv squared over r equals, in this case, the sum of the forces. I've just called it T. It's asking us for the tension force, so T just equals the mass of the object is 2 kilograms. The speed is 3 squared over 1. So that's 18 newtons. The tension is going to be 18 newtons. Then it says what happens to the string, what happens to the rock if the tension breaks. Like maybe the string, it's like, I don't know, maybe it's something really weak, like thread, and it can only withstand 50 newtons of force. So you're trying to spin it faster, it doesn't have enough force to withstand this, and it breaks. What will happen? What's the trajectory of that stone? A lot of people want to say it's going to fly outward because you feel like you're being thrown outward when you're in some kind of a circular motion. But what will actually happen to this object is that it will fly tangential. So the path it takes, if the string breaks, when string breaks, basically it's like this. When the string breaks, there's no force acting on it, right? There's no more force keeping it in a circle. So its inertia is just going to make it do, it's going to say, well, if there's no force on me, I have inertia, I'm going to keep doing what I was doing, which is moving in a straight line at a constant speed. At this instant, when the string breaks, I was moving this way. I'm just going to keep moving this way at 3 meters per second. So the path to take from the string breaks is tangential. I'm going to call it tangential to its circular path. And it maintains that constant speed of 3 meters per second, as long as other factors don't influence it, like friction between the table and stuff like that. So really keep in mind that you're not actually being flung outward. It's kind of an illusion based on the fact that this ball is always wanting to move tangent to the circle, but the string is always pushing it in like this. So as soon as the string isn't pushing it in, it's just going to do what it wants to do, and that's fly off tangent to the circle.